Today, we're digging into a story that honestly feels like it's straight out of a movie. We're talking about a math problem that was declared completely impossible to solve for 2 entire centuries. And, well, it might have just been cracked.
So think about this for a second. For 200 years, a whole area of mathematics was built on one fundamental assumption, that there was a hard limit, a point where finding an exact answer was just impossible. But what if that limit wasn't a wall, but just a horizon we hadn't figured out how to cross yet?
All right, let's start with the problem itself, the impossible equation. We're talking about the legendary and notoriously difficult challenge of the 7th-degree polynomial. You know, for ages, mathematicians were on a roll, wrestling with these polynomial equations. 2nd degree, 3rd degree, even 4th degree. They were all eventually conquered. But then, when they got to the 5th degree and higher, they hit a solid brick wall, a total algebraic dead end. So what exactly was that dead end? Well, it's known as Abel's 200-year-old rule, and it's the reason a whole field of math basically stood still on this particular problem for so long. So check this out. Way back in 1824, a mathematician named Niels Henrik Abel proved you couldn't get a general solution for these equations using standard methods. And for the next 200 years, the entire field just pivots to approximating answers. Then, bam! 2023 happens, and Professor Mourad Sultan Ezouidi publishes his work claiming a complete, exact solution. I mean, that is a massive claim.
So what did Abel's big theorem actually say? It states there's no general solution in radicals. Now that's the crucial phrase right there. Think of radicals as your standard math toolkit. You know, addition, subtraction, taking square roots, cube roots, that kind of thing. The theorem never said a solution was absolutely impossible, just that it was impossible using those specific tools.
So why did those tools fail? Well, for one, the internal symmetry of these equations was just way too complex. The number of terms you had to keep track of just exploded, forcing everyone into making estimations. And, over time, that practical limit became a philosophical one. It was just accepted as an unbreakable truth. And that brings us to our protagonist. Let's talk about the challenger to a theorem. This is really the story of one mathematician who just refused to believe that impossible was the final answer. Professor Mourad Sultan Ezouidi looked at this 200-year-old barrier and saw something totally different. He didn't see a fundamental law of the universe. He saw a boundary that we built ourselves from what he calls an incomplete understanding. He basically believed the classic tools were the problem, not the equation itself. And you can really feel his personal drive shine through in this quote from him. He wrote, "But I have never accepted that limitation." That's the kind of conviction you need to challenge 2 centuries of mathematical consensus.
So how does he claim to have done it? This brings us to part 4, solving with new tools, and the core idea that lets him get around those classical limits. Now, this is the really clever part. The goal wasn't to prove Abel wrong. The claim is that Abel was right, but only within that limited framework of radicals. The real solution was to build a new framework, a whole new set of rules that could operate outside of those old constraints. And the contrast is just stark. Where classical methods said impossible, Ezouidi's theorem says exact solutions. Instead of radicals, his method is based on something he calls recursive discriminant structures, which is basically a new way of organizing the problem into these repeating, manageable layers. But the biggest leap is in accuracy, from just approximations to a claimed 100% verifiable algebraic solution. So, how does this new method actually work? Well, you can think of it in 3 big steps. First, he reorganizes the polynomial into those recursive layers. Second, a special transformation is applied to each layer that uncovers these hidden symmetries. And finally, those symmetries generate a chain of identities that let him pull out the exact roots. It's really all about finding a new kind of order inside the chaos. So this all leads us to the bigger picture in our final section, the future of algebra. Because if this new method holds up, what are the implications of solving the unsolvable? We're talking about a huge shift in mathematical philosophy. The old view could be called mathematical fatalism, this idea that some problems just have these unbreakable limits. This new view is all about symbolic discovery, the belief that every single equation has an exact form, just waiting for us to find the right tools to uncover it. And at the heart of this entire claim is one number, 100%. The goal is total algebraic accuracy. In pure mathematics, that jump from a close enough approximation to a perfect, exact answer Well, that's everything. It's the Holy Grail. So what could this mean for the future? I mean, it could redefine solvability itself. It could create a whole new paradigm for this class of problems. It suggests that math still has these vast, unexplored frontiers. And maybe most inspiringly, it suggests that impossible is often just a temporary milestone, waiting for someone to blow right past it. Which leaves us all with a final, pretty provocative thought. If a mathematical truth that stood firm for 2 centuries can be redefined, what other accepted limits, in science, in technology, in any field, are just sitting there waiting for someone with a new perspective to come along and break them wide open?